Okay, I get my signal, so I start. Can you all hear me? Okay, perfect. Yeah, thank you all for coming to my session on making Java more dynamic and runtime cogeneration for the JVM. Those might seem unrelated, but what I want to talk about today is more or less Java's type system, which is a strict and static strong type system, and how it can sometimes be in the way, and how code generation can help to overcome this being in the way sometimes. So in order to make this make sense to you, I just want to start out with an example that you probably all know, more or less. If you look at this code, this probably seems sort of familiar, right? What I try to mimic here is Spring Security, more or less. How Spring Security works, for those that don't know the framework, is more or less that you have an annotation, here I call it secured, where you can assign a value to a property, here called user. And then we have a user holder that defines what user is currently logged in. So if you want to log in a user in our application, we would assign the static field user to, for example, resemble admin. It's of course an oversimplification. Spring Security doesn't actually work like that, but it's fairly close to how the base idea is. And if you want to work with this framework here, then you probably would use it like that. You have, you write on your business application and your customer says, okay, I want this one button, and if I press it, the whole database should be removed, or not the database, but all data. And yeah, this is fairly sensitive, right? You don't want anybody to be able to press this button, so you want to have a tight check. So you want to check at the method level that the user that is actually logged in at the point this button is pressed is always administrator or admin. So how do you achieve that? Well, you would have a framework like Spring Security being part of it, which takes a type like service, the one we defined, and basically applies this annotation for you. So you want that every method on the service class is getting secured by the user of your framework. But there's only one problem. Well, the framework promises to basically secure any type of your class, of your application, right? You write the service class, but you do not write Spring Security. Spring Security is external to the code you write. And this is a problem in statically typed languages, because how would the framework know the service class, right? Those are two different jars. This upper one is Spring Security, or any generic security framework you can fill in for that. And this one down here, this is your application. And we have a problem that your application knows about Spring Security, but Spring Security doesn't know about your application. And this is where runtime cogeneration comes in, right? So at runtime, those two libraries, your application that you wrote and Spring Security, they come together, and then they can actually do something like securing your service. And in order to do that, the code has to be changed. We have to actually implement some security check inside of the delete everything method, but we can only do this at runtime, because at compile time, the security library doesn't know about the framework or the application that you have written. And this is why code generation is pretty important in the Java space. It's omnipresent. I'll show you later where it's used approximately, but it's something you probably all have worked with in the past, even if you might not have known that. How can we implement the security check? Well, easiest and most straightforward approach would be to just add a security check inside of the method that we want to secure. Up here, right, we just check, is actually admin equal to the user that is currently logged in by being set on the user holder? And if this is not the case, we throw an illegal state exception. The user is not the right one. And as a consequence of that, we will exit the method. We will not ever execute the code that is represented here by the comment delete everything. We will not delete everything if the wrong user is logged in. This can be done by redefinition. We can use a build time instrumentation for that sometimes. We can use a Java agent for that. Talk about agents a little bit later. Or the more straightforward, or the less straightforward approach, but the more common one, is to actually create a subclass. This is how most frameworks work. This is how Spring Security approximately works as well. It creates a subclass, right? If you have a Spring Bean and you have annotations like that, the class of your instance will not be the same class as you have defined. There will be a subclass of it that Spring created for you at runtime, where we have the security check in the beginning of the method in a way, and only if the security check passes, we call the super method that then contains the original implementation of the method, where we delete everything, right? This is more or less a Liskov substitution, and this is working well in Java because we have static types. A secured service can be used everywhere where you would use a service. You don't have to know that it's a secured service, you can just substitute it, right? This is how Java works, right? Let's do some Java 101 though, to be sure we're all on the same page. We all use these languages, right? Any of them, Java, Scala, Groovy, JRuby. And how can they all run on the JVM? It's thanks to Java bytecode. Java bytecode is a common format, and if you use an appropriate compiler, you translate into this level. This is how languages can interoperate. The Java virtual machine actually doesn't know about Java, the programming language. It's a foreign concept to it. It only knows about bytecode and how to run bytecode. Sometimes even Java doesn't really match what the JVM does. Like, for example, boxing doesn't exist on the JVM level. Or generic types, very famous example, do not really exist on the JVM level, only like as metadata. They're not enforced. However, thanks to this intermediate format, we can do something in Java that is not that easy, at least in other compiled languages like C, for example, C++, where we compile to machine code directly and not to bytecode. We can, I skipped a step. Yeah, this bytecode is not executed though. It's only loaded into the JVM by a class loader, and then it's interpreted. Some JVMs don't even have interpretation, and then it's just in time compiled. And as a consequence of that, we can actually just generate bytecode from anywhere. We don't have to use a language like that. We can use frameworks and libraries that at runtime generate bytecode, which is a very well-defined format, and we can just run this bytecode just as if it was written in Java source code, right? And also, we can even read bytecode. And this is how we can do these manipulations. We can go into a method, we can read it, we can see, okay, there's an annotation that says secured. Then I just go into the method and I add some instructions at the beginning. And as a consequence, we have changed the program to actually do what we expect it to do, to be secured. And we can run this inside the same application that is the Java program that we started to write in the beginning. So we have the cycle, right? We start a program. The program starts by looking at its own code and rewrites the code appropriately on startup, for example. And then we just execute it, and it does what we wanted. And a very nice side effect is, as I mentioned before, we don't have to worry about compatibility. If you had machine code in the middle, you wouldn't know how the machine code looks like. It could be an architecture you don't even know about. But thanks to the bytecode format, we don't have to worry about that. And thanks to the just-in-time compiler, we don't even have to worry about performance too much, because the code we generated is basically processed by the just-in-time compiler later, and it is optimized in a way that we don't really have to worry about how the exact bytecode representation of the logic we want to implement looks like. Okay, if you're not familiar with the concept, one first thing you might have to get over in the first place is, people say this is what reflection is meant about, right? Java already has a mean of dealing with types that aren't known at compile time. This is reflection. We can look up types, we can look up methods from types, and we can look up and we can invoke these methods later. So we can already deal that. We could, for example, say we have an interface named secured method, right? And the secured method interface has a single method which takes any generic array of arguments and then invokes a method and does the checkup explicitly. It uses reflection to look up the annotation. It then checks the current user against this annotation value and only invokes the original method if this check passes. However, if you look at these declarations, you already notice that they're generic. They don't really have any type safety left. And this is the beauty of not using reflection but code generation. You can actually or allow the user of your security framework to use its own types. You don't have to basically depend on framework types that abstract away all type safety that the user has introduced in its own program. With reflection, you cannot do that. You cannot check at compile time if the reflective method invocation will actually work at runtime. You give this all up, and you can't get it back. So runtime code generation allows you to preserve type safety. So in a way, runtime code generation is a mean of dynamic typing while preserving static typing, if you want to put it like that. What you could also argue is that runtime code generation has a significant overhead. You have to have infrastructure. It sounds complicated. So why not put it into the method yourself? Why not it's just 3 lines of code, one just being a brace? And why not put the security check in the methods directly? Well, of course, at best, this only ruins your testing environment because you have to set the security context when you just actually want to test if the delete everything method works. On second look, it also basically distributes logic inside your framework. This is infrastructure code. This is a cross-cutting concern security, right? You don't want to have this inside the method necessarily. You want to make this in a declarative manner, and code generation is a great way of achieving that. Yeah. And think about dynamic languages. How do dynamic languages work? Let's say we write our application in JavaScript, and let's say JavaScript had annotations. There actually are frameworks that parse comments to extract this sort of information. But let's say we have JavaScript and we have a framework like that. We can already do this. We can just hand any service object inside to this method, and we can just replace it by redefining methods. So in a way, we achieved something that you can do in JavaScript in the first place, something that is already very present in dynamic languages, but without giving up type safety. So code generation is a way of achieving something that you can normally only do in dynamic languages, but you get the good parts as well. You get the static type safety. I mean, that's why we like Java, right? It's the static typing. Some call it verbose, and sometimes it's in the way, but often it really helps us to write good, well-functioning Java programs. Okay, so this is duck typing, right? Okay. So, where's this used today? Everywhere, more or less. Spring, I mentioned already, Spring Security. How does transactional, how does the annotation work? Well, the method is instrumented again. It's rewritten to, at the start of the method, open a transaction, and at the end of a method, close the transaction. Hibernate. How does Hibernate know that you update a bean value? Well, it adds some code to the method, to the getter or the setter, to actually load a value if it is required, or to store a value once you save an instance, so that Hibernate can keep track of a state of a bean. You just annotate the methods. Hibernate then adds the code that checks if you made changes to that bean. Mockito, also a very good example for code generation. How does Mockito achieve that once you call a method, nothing happens? Well, it overrides the method to not do anything. Or only if you basically tell Mockito to call the super method, it will then apply the original code. But otherwise, Mockito gets control of the method call by adding its own code to the method. And I can go on like that forever. Like Play is a very good example. It's basically 50% code generation. And even the OpenJDK uses runtime code generation to implement Lambda expressions. So it's something, at least with Java 8, you all use every day. Okay, so great, a new tool, right? So you can just go out there and start using code generation for everything. And unfortunately, some people are tempted to do that. So I have this one slide, disclaimer slide, so that I'm not blamed in the end, when not to use code generation. Okay, first example, let's see here. We have a method that computes something. We multiply a value I with a constant that we get from some field. A C programmer would say now, well, this is not efficient, right? We have a constant value, we can just copy that into the method. Sometimes the Java C compiler actually does that. But there are frameworks out there that claim to improve your code by doing this sort of bytecode optimizations. However, the JVM already knows how to optimize these things, and it uses code generation for that, but on a very much lower level, which is the just-in-time compiler. And as I said before, using code generation in Java, you don't have to worry about performance. It's already done for you. Another popular example for using code generation is to use reflection. And this is historical. If you look that up on the internet, is reflection slow? You will get a lot of answers saying yes. As a matter of fact, it is not slow. Reflection has improved since Java 1.3 and 1.4, where these answers mostly come from. But historically, like cglib, which is a famous Cogeneration library, it offers something called fast method invocation. However, the JVM already discovered Cogeneration for itself. In the beginning, when you call a method reflectively, the JVM uses the native interface to invoke a method. But this is slow. It's not slow because native calls are slow as such, but it's because the just-in-time compiler doesn't know what to do with native code, so it can't optimize it. For example, let's say you call a method that is empty. The just-in-time compiler could just remove this method call altogether. You wouldn't have to do it. You would save that time. If you do it via reflection in the beginning, it's done via native interface, and you don't know what happens, right? It's native code, so you can't remove it. That's the problem. To overcome that, the JVM already implements Cogeneration, however. If you use a hotspot VM, there's a value called inflation threshold, and it's set to 15 at default, and causing the JVM to generate bytecode that represents the reflective method call on the 15th call. So even the JVM, even before Java 8, uses Cogeneration in order to implement some sort of dynamic behavior, dynamic typing behavior, which is their reflection. Yeah, so the jitter compiler knows its job. This is just the giveaway of this slide. So don't optimize bytecode. Don't invest in products that claim to optimize bytecode. There are a couple out there in the Java world. So yeah, it's not that bad. What is expensive, however, is reflective member lookup. That costs the time that people normally measure when they compare reflection to native, or not native, common method calls. So yeah, this is just not true, right? Okay, I mentioned bytecode. So, and we need to do code generation. How can we achieve that? Well, the easiest way would be to just generate bytecode. Bytecode is bytes, so it's basically a byte array. And yeah, it could be that easy. But of course it's not. The JVM enforces its own view on what a program is. And we have this rather declarative style in the Java source code. However, bytecode looks a little bit different. This is an example of how 1 plus 2 looks in bytecode. The JVM is a stack machine. Stack machines they exist in hardware, but they're not that common. Most machines are register-based, at least most machines we use in our daily life. But at the time when Java was created, stack machines were a good way to abstract bytecode because stack code takes less space. And Java originally, the language of the internet, you want to write applets and all these things. So you have to transfer bytes over the wire in a quick manner. So the bytecode itself should be as compact as possible. And a stack machine always has an implicit target. It always pops or pushes values from a stack, so you don't have to add addresses. That makes it very compact. So good choice back then. Today, if you talk to the JVM engineers, they're not all happy with bytecode, how it looks like. But it's legacy. You have to live with it. But how is this method executed? Well, stack machine, right? If you remember the university days, how do these work? You push and you pop values to a stack. And we execute the program from the top to the bottom. So we first push a constant 1 onto the stack, then we push the constant 2 onto the stack, and then we add both values, ending up with 3. So how do we implement the return statement? Yeah, well, we have the 3 on the stack now, so there's an instruction for that, iReturn, that just pops the 3 from the stack and returns it to the caller of the method. And it's called bytecode because all of these instructions have their own byte that represents them. So if you compile this method, and you can open the class file that you created, you will have these 4 bytes in a sequence there. Other than that, just Javac does some minor optimization, so it would just merge 1 plus 2 to become 3. But you get the idea. This is how a class file looks like, and this is the byte array. These 4 bytes would be contained in the byte array that you would create if you wanted to create a method at runtime dynamically. And you can do that pretty easily using libraries like ASM. ASM is a great library. It basically takes these instructions here that we see. These 4 instructions are those instructions. They are so-called opcodes. They're mnemonics of what these instructions do. And if you get a method visitor, you can basically visit the instructions in the order they should be executed. And ASM will take care of most of the infrastructure work, like maintaining a constant pool, which is an important concept for a class, and so forth. There's this visitor API, and there's a little bit more less performant but more flexible tree API, and you can do that. Like, this is easy, unless you get it wrong, because then ASM cannot warn you about these errors. So you can just shuffle these instructions around, for example, and at runtime you will end up with the verifier error at worst. Or even worse, you might push this iReturn up two steps, and then you have a method that returns 1 instead of 3. That's not what you want, right? Yeah, and that's why I'm here today, more or less. I wrote a framework that makes it easier, hopefully. Before that, I maintained a framework that also makes it easier, which is cglib. I didn't maintain it myself, obviously, but I did some patches around until I got frustrated, and then, of course, you write your own framework, right? Yeah. However, sometimes bytecode ASM is great, but it gives you full freedom. You can do everything. But it requires you to know bytecode, which is the stack metaphor. We have the JVM's type system. For example, the JVM doesn't have the same notion of integers as the Java language does. On the JVM stack, for example, there are no shorts, there are no booleans in the JVM altogether. So you have to learn something to actually be able to apply it. That's not always good, because then you might have a project where you use ASM and only some members of the team can touch this part of the code. And it requires a lot of manual work, if you want to do it efficiently, at least. There's some things that ASM can take care for you, but there's things like stack sizes. You have to actually tell the JVM how big a JVM stack needs to be in order to be able to execute the method. And you can't just always say, okay, it's probably 100 is a good guess, so it will never be more than 100, but that will cause you at runtime. So manual ASM, while giving you flexibility, it takes a lot of energy. And yeah, as I said before, ASM itself doesn't allow you to enforce type safety. You can get things wrong pretty easily. And you are in danger of producing verifier errors. And yeah, and as I mentioned, bytecode itself is a little expressive. 1 + 2 looks much nicer in Java source code, right? Than it does in bytecode. And yeah, then again, we have low overhead. And ASM is currently more popular than BCL. It's used by the OpenJDK. It's currently public API. I wouldn't bet on it. I think in Java 9 it's going to be hidden away in a Jigsaw module. But if even the OpenJDK bets on ASM, it pretty much settles the deal between ASM and BCL to be the winner of this race. And there's one problem with ASM. There's a versioning issue. In version 3, a lot of things were interfaces that became abstract classes. So unfortunately, if you look for ASM issues on Stack Overflow, for example, the top 50 will be versioning issues. So also be careful. The recommendation is officially to repackage ASM into your namespace. All right, so much about ASM. The library I wrote is called Byte Buddy. And if you look at this code here, I hope you can all understand what the code is doing. Well, but let's step through it. Byte Buddy works by more or less creating something that is a configuration instance, which is named Byte Buddy. And then we tell it to subclass something. In this case, we subclass object. Then we identify something, identify methods. Here, any method that is called toString. For the object class, this is only the one method that is called toString. You can hypothetically define several methods with the same name, but then you can be more precise about it. It's basically up to you. And we want to intercept these methods to return a fixed value named just hello world. Then we can make this class and load it into the class loader of the enclosing context and get the loaded class that we just created. This is then already the Java reflection API. And this, of course, then, if you do an assertion, we create an instance, we return hello world for you. Obviously, this is easier to use and more safe to use than ASM is. Internally, again, Byte Buddy uses ASM as any framework, but you save yourself the troubles of understanding all the gory details of bytecode. This is, of course, still quite boring, right? So let's look at something more flexible. Again, we want to subclass object, and this time we want to intercept, but not by defining a fixed value for the toString method, but by delegating to a class or a method rather. And this method is the intercept method. This looks a little bit magical at the first look. You can be way more precise using the framework what method you want to delegate to. But the simple rule is that if there's only one method, it will try to delegate to this one method. Otherwise, it will try to find a best method, which is in a way very precisely described in Java docs. But yeah, this is good enough for us now. Again, we return hello world, and this is of course the same result. However, this time we can create this result dynamically. We could return anything that we just compute, because every time on this dynamic types instance the toString method is called, this method is instrumented, like with Spring before, the Spring example before, to actually go to the intercept method here. So in order to make this a little bit more interesting, we can actually define arguments, and these arguments are added using dependency injection. So you declare what you want in order to instrument a method, and Byte Buddy will inject it for you. In this case, for example, we create a delegation that then says hello world from method get name, which is then toString, and we could apply this, for example, to override other methods, and it would do the same thing as long as it can return a string. There's a big advantage with using annotations. It's a little known detail about the Java virtual machine. When an annotation value is not found by a class loader, it is simply ignored. So even though you use an annotation that is Byte Buddy specific, the created class that we create here is not dependent on a library. So you can create a class wherever in your application and then just load it into any class loader. The origin annotation is simply dropped. It's unused metadata. A lot of other frameworks like cglib, they use interfaces in order to do the delegation, and with interfaces that's not possible. So yeah, it's really Cogeneration without leaving traces of the framework that created it. It could just be Java code or Java source code that created this class, just that we don't have to do it explicitly. Yep. There are a lot of annotations in Byte Buddy. We just saw the origin annotation, which allows you, for example, to inject the original method. Using this original method, for example, we could extract the annotation on the method, the secured annotation from before, and could do the security check. And then we have this one, the supercall annotation, which is also injecting basically a callable that allows you to invoke the original method. So already now, we could implement the security framework from before. We could read the annotation using the origin annotation, and we could then invoke the original method in case that our security check passes using the supercall annotation, and you would have implemented the security framework in more or less 5 lines of code. And yeah, so I hope I can advocate to you this is a sensible approach. Today we use a lot of infrastructure frameworks in order to implement such things, but we don't have to. It can be much easier. But there's more. There's a feature in Hotswap that's called Hotswap. Hotswap, you might know from debugging, allows you to replace a method body with another method body at runtime, and even after you loaded the method. And Byte Buddy can make use of this feature, or anybody can, but there's a feature built into Byte Buddy that allows you to do so. So let's say we have a class foo that has a method bar that always returns bar. Then you can create an instance of foo, and then use Byte Buddy here to redefine foo at runtime. You can redefine it to return hello world. And as a matter of fact, if you use this using a so-called class reloading strategy instead of the class loading strategy from before, you can achieve this. And obviously, this is something you should use carefully, because this is not necessarily someone your coworkers won't appreciate you, right, for doing that. Necessarily, because it makes things hard to debug if this is suddenly hello world. But obviously, if you don't change the original implementation, but you just enrich it, Hotswap can be a very, very useful feature, not only for debugging, but also in production service. Because you only redefine a method once. It's not so bad. Basically, the hotspot throws away all its optimizations concerning this method and redoes everything. If you do this with Bootstrap application, you didn't lose anything. And there's one downside of Hotswap, and that is you cannot define new methods in a class. You can only change methods. And this makes things sometimes difficult. Because internally, Byte Buddy, of course, or the Cogeneration framework has to keep track of the original code that you want to instrument, and you has to save it somewhere and does that in a new method. However, there's a JEP, number 159, called Enhanced Class Redefinition, which is basically implemented already. It's still waiting for approval or merging. I'm not sure if this will ever be a feature. But if it is, this can really allow us to do different things in Java in the future. Because then we can actually just hot swap. We can more or less turn on and off the security framework by really erasing it from the methods, like literally erasing it. So we'll see what the future holds. A better way of achieving the same feature is, I mentioned in the beginning, a Java agent. A Java agent is more or less its own jar. Let this above jar be your actual application, where you define something to happen, and then this down jar is an agent. An agent is more or less a class with a pre-main method and not a main method. A pre-main method works in a very similar way, though. The pre-main method is invoked by the Java virtual machine before the main method is invoked. So it's a program before the actual program. It's not only that, though. A pre-main method can request different parameters in its method, which is, first of all, arguments that are specific to this Java agent, and then it can request an instance of the so-called the instrumentation interface. An instrumentation interface allows you to access some internals of the JVM. And it allows you, for example, to define class loader interceptors. These class loader interceptors are then activated, or class file transformers they're called, activated whenever a class gets loaded in your JVM. And since this happens before the invocation of the actual implementation, you can, for example, say, every time a class is loaded, I want to get the chance to, for example, implement the security annotation that I mentioned before. Byte Buddy also takes care of the ugly parts for you by offering an agent builder. So far, everything I've seen, even with other libraries like Javassist, defining and building an agent is quite a hassle. It takes time and it is very error prone. So I try to make this easier, and I hope I achieve this. This is an example. Here we take an agent builder and we say, okay, we want to rebase any type named foo, like the one above, and then we want to transfer that type. And this part here, the builder part, is basically the same API as here. We take a method and we intercept it. And then we install this transformation on the instrumentation that we get for this Java application. So now we have basically achieved the same thing, only that now, using the instrumentation API, we can define new methods on classes. So again, we have basically here all the ingredients we need to implement something like a security framework, like a logging framework, anything you like. And it's very little code. It literally fits on a slide, right? Okay. So the world, how I see it. Today we have very heavy integration frameworks. We have Spring, we have Hibernate, and all these frameworks require you to basically code against the framework. It doesn't allow you to write plain vanilla Java. It helps a lot, they help a lot, but just in order to, for example, enable Spring security or Spring transactions, you have to drag in the entire Spring dependency, right? And I don't say Spring is a bad framework, not at all, but sometimes you don't want that. Sometimes you just have a very simple use case where in production you want to enable logging for certain methods, right? So why not use agents for that? It's not that easy. It's not that hard to implement an agent that fits your custom needs. You don't have to write a library that does everything. But you can write small libraries that do one thing and do that well. And that's more or less, the idea that works very well for Linux, for example. Why not have a specific logging library that just allows you to annotate a method and say, whenever this method is invoked, I want to write something to my log. Or I have this other framework that says, whenever this is transactional, I have my custom transaction implemented. And you just pick the ingredients you want. Today, we don't do this because we use the subclassing instrumentation, right? We have to have a framework that creates classes for us, creates instances for us, and does all the cross-cutting handling in one single step. I say it would be better to not do that, to have the integration framework come to our code, to more have something like that. We just write plain vanilla Java, and we just add the ingredients that we actually require. And of course, this is a long, long shot of how Java applications should be built, and it's my opinion, of course, and you're very welcome to challenge my opinion. But instrumentation and code generation is a great, great tool to make things more easy in that sense. And I like to call that plain old Java applications. You just write something, and the integration framework has to take care of getting in between where it needs to be. And of course, that's not like this is not a perfect tool for anything either. But for some and many use cases, this is a good way of doing things. One thing, if you talk about instrumentation, is Android, which is also Java in a way, but it's not really Java, right? Android has its own VM, it has its own bytecode, and I can tell you Android bytecode is significantly more complex than Java bytecode. It's, for example, a register-based machine. The just-in-time compilation works much different. And I understand why they do it, why they have to do it. They code for entirely different hardware. They don't want to have this whole translation from stack machine to register-based machine only when the applications actually run. They want to have some optimizations done before the application is actually deployed. Simply because Android devices are killing and firing up applications all the time, while Java applications normally have a longer lifetime. And we can, when we code against the Java virtual machine, we have the stack machine and the just-in-time compiler. With the DEX format, we have a register-based machine, which is, however, still standardized. However, recently there was the ART runtime came to Android, and ART basically discarded bytecode altogether. Not altogether, but the bytecode is now transformed into machine code once an Android application is installed on the phone or the device Android is run on. So you suddenly only have machine code at runtime now, which does not allow you to read bytecode in a standardized way anymore. However, you can still create subclasses, and there's a DEX compiler that Google delivered under Apache 2.0 license, which is the same license Byte Buddy runs in. So Byte Buddy, since end of last year, supports Android subclassing, so at least a limited set of options. And so far as I know, it's the only framework, more or less, that supports that. So if you want to do work like at least limited instrumentation work in Android, you can even do that. Finally, the slide I wouldn't have if it wouldn't be in my favor. Bytecode is a lot about instrumentation, is a lot about performance, right? So I wrote a JMH framework comparing the usual frameworks. I wouldn't say Byte Buddy is yet the usual framework, but cglib and Javassist are, and the Java proxies, which are delivered with the JVM actually, but only allow you to override interfaces. So it's a very limited scope, and you can make code generation very performant if you want to, and if you look at how the JVM behaves, because in theory the JVM is this magic box where you can just throw anything at it and out comes great performant Java like machine code, right? But in reality it's not true. The JVM expects sometimes certain patterns, and if you compare how you can generate code, then sometimes code ends up being more performant if you do it in a certain way. And if you look at the machine code that JVM generates for your bytecode, then you can actually optimize quite far. So, however, there's always a trade-off between generating classes and generating performant code. It's like the just-in-time compiler, right? It also sometimes has this different levels where it sometimes says, I want to generate machine code quickly, which is less performant, or sometimes it spends a lot of time to generate the machine code, which is then super performant. And for code generation tools, it's more or less the same question. And Byte Buddy is not as sophisticated as the just-in-time compiler, having tiered compilation or something. So it always goes in favor of actual runtime performance, assuming that you probably only spend little time creating classes and a lot of time using instances of these classes. And you can see this 3B benchmark is executing a method of a class with 18 different methods, where it simply calls the super method, which does some very basic logic. And just by doing the code generation efficiently, and it's a lot about avoiding boxing, for example, you can get down from 19 nanoseconds to 2 nanoseconds, even though treat benchmarks always with care, because benchmarking on the nano level is difficult. You really have to look at what you're actually measuring. I hope I did the best I can to actually make a good benchmark. But yeah, it's on GitHub, so find it and again, challenge it. All right, I'm 10 minutes early. Thanks for coming, first of all. My name is Rafael. You can find me on Twitter, on the internet. You can find Byte Buddy on the internet, of course, on GitHub. Please tell everybody you know, tell your friends, your wife, I don't know, your parents, everybody, because it's a young framework, so it can take some publicity. And yeah, thanks to my employer for bringing me here, to allowing me to be here. If you're interested in Norwegian software market, please find us on buve.no, and we have a blog and we have a Twitter. If you have questions, I have 9 minutes left. So thank you all for coming, and yeah, thank you. Are there questions? Yes?
So I think I know the answer to this one, but how does Cogeneration impact debugging?
In a way, code generation doesn't have source code attached to it, right? Generated code doesn't exist in source code, so a debugger doesn't have a source code file or a line number to go to. I hope it's not too much marketing for a framework, but it copies the debugging. Or if you override a method, for example, for an agent, you instrument a method. Byte Buddy copies the original method into another method that is private to the class. And if you invoke the super method, it invokes that private method instead. So it's transparent to the outside. But it also copies all the debugging information. So a debugging client would just jump to the same source code location and have the same debugging information available even after the instrumentation. So of course you would see it on the call stack, right? But you see bridge methods on the call stack, but they're marked as synthetic. So most IDEs even make them disappear. So it's not so bad. If you can debug code that is instrumented, even heavily instrumented, because the original code will always be preserved in its original form, and most IDEs take care of the rest and hide it from you. So it's not so bad. Yes?
What you can do is to generate the code corresponding to the Byte Buddy code for the code that...
Yeah, you could basically have an additional decompiler. However, how I see code generation should be the absolute minimum. The code generation should more or less create a binding between the original code and the code of your framework, where the framework code should be implemented in plain old Java. This is, for example, where Javassist, which is another famous code generation framework, diverges, where you do basically everything in strings, and then you compile these strings to Java bytecode without it's not actually Java, it's a Java dialect in a way, without the debugger knowing that the source code exists. But yeah, it's a difficult question in a way, but as I see it, so in my experience, by keeping the generated part to a bare minimum, it's just the glue between the framework and the user code, you can hide it as so well that most users will never notice it. But yeah, it's a valid point. It's just additional work.
You still throw exception, by example, if you take your example.
Yeah, but
You still throw exception.
no, but the thing is, this exception, when I go a couple of slides back, if you have a delegator, for example, here, this exception would be thrown here, right? And this is a normal Java class with source code. So you can actually go to the exception, and you will see that there's some code that says if method annotation get user is not equal to admin, and then you can basically know what it happens. Only what you will see is this additional binding. You have this synthetically implemented, in this case, toString method, which is as much as calling the static method.
Yeah, but in that case, you lost specialization. write one intercept for int, one intercept for long, one intercept.
Yeah, but yeah, there's an annotation for that as well. You can just return object, and the callable will just return object as well, right? So internally, Byte Buddy casts it, assuming. But if, of course, if you return invalid value, it only goes so far. You have always, yeah.
You have boxing.
Yeah, in that case, you have boxing. That's right. But also, you can actually. There's also a way to avoid that by using compositions. Basically returning void from the thing and then calling the super method internally in the generated code without the boxing. But yeah, you're right, of course. I mean, the abstraction is not perfect. Like, I would say any abstraction is imperfect. But you can keep it to a minimum, I argue. But you're right.
Did you take a look to Java long invoke?
Java long invoke.
Invoke package.
So,
Java long invoke.
yeah, the invoke, Java lang invoke, yeah. The method handles are, of course.
Because you can do most of what you are doing with method handlers. And basically, a method handlers is cheated the same way the Byte Buddy.
It is true, but still, I'm not entirely agreeing with you on that. Because, yeah, you can use method handles, but method handles are way more complex, I would say, than this API. Yeah.
Externally, I don't.
Yeah.
Inside Byte Buddy, instead of generating,
Yeah.
instead of using ASM, you can use method handler.
It is true. I could have done that, but I did. Yeah, but of course, method handles or the entire Java lang invoke part are offering entirely new possibilities. As far as I know, there's even speculation, or not speculation, there's ideas about having something like invoke dynamic. There's an idea to introduce a bytecode construction called class dynamic to actually make class generation JVM. We don't know where it goes. I heard a talk once at Java 1 about how this might affect the future, how you can maybe even take care of Java proxies, because we'll see, probably, maybe not, but who knows? Or I don't know, maybe you know more about it?
No, class dynamic is that it's another thing. It's more something like if you want to do, if you have generics and you have primitive type, and sometimes in the future you want to have a list of int,
Yeah.
by example, you need something which, for a name, is able to represent the concept of list of int.
Yeah.
This is class dynamic. It's more related to the how to see a name or a Mongol name as something that can be decomposed by the.
Yeah, there you go. I can't add anything to this, but yeah. As I know very little. I just heard it on the side once, but yeah, probably you have a good source for it. Okay, but thanks for the feedback. Yeah. 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 Yeah, it's partly true. You can actually run AspectJ with an agent as well, but I think AspectJ doesn't seem to be very popular with many developers, and I think it is because you have to more or less learn a new language, which is the language of aspects and this join point and so forth. It is true. AspectJ is a very powerful tool, but I understand why a lot of people hesitate to drag it in, because it is very heavy. It's not a Java DSL, or it's not something that is pure Java. It has its own, expression language, if you want to call it like that. It works very well. I know that, and I'm aware of it. And more or less, I'm trying to advertise aspects. I just try not to sell them as aspects, because people don't like aspect-oriented frameworks for Java or tend to reject them. Yeah, but you're right. Thanks. Other questions? Yes. Yeah, but there's other methods. Basically, the named thing I showed is just it's a functional interface, so you can implement it in any way you like. You can just say it has a certain annotation on it, for example, and then it's more flexible. It's for the sake of simplicity. But yeah, of course, I mean, you don't have. It's not a perfectly type-safe way of redefining classes either. You don't, for example, you don't know about return types and so forth necessarily, but in a way, at least Byte Buddy tells you right away. Reflection tells you when it's too late when you try to invoke the method not at bootstrap. So yeah, but of course there's room for error. All right, my time's up. Thanks for filling the last 9 minutes with questions. Thanks for coming.